topics. So, consider this one as a course, and I am discussing about discrete Fourier transform. The contents what I am going to cover in this class is defining discrete Fourier transform, how to compute endpoint DFT, computation of endpoint IDFT. IDFT means inverse discrete Fourier transform, and what is the relation between endpoint DFT and DTFT, that means discrete time Fourier transform. So, coming to the definition of a discrete time Fourier transform, the name itself tells that this transform is discrete. Earlier we have Fourier transform, but that will be only for finding the frequency components of a continuous time signal. When we come to discrete, it will not useful. So that we are going for discrete. In this discrete Fourier transform, we consider the sequence as a signal as in a sequence. It is in a discrete time sequence. So, applying discrete Fourier transform on the discrete sequence will give the frequency coefficients. So, let me define the definition of discrete Fourier transform. It is a mathematical tool which is used to compute the discrete frequency domain from a finite discrete duration sequence. That means, if you consider this one as in single board, just transforming discrete time signal into discrete frequency, time domain to frequency domain. Coming to the computation of endpoint DFT of a sequence. So, here what is endpoint? Here we are taking the number of samples. Based upon the samples number, we are going to define discrete Fourier transform. That is why we call endpoint DFT. It is also defined like this: if x of n is in a finite duration time domain sequence with a duration of n samples or a range of 0 to capital N minus 1, then the DFT of a sequence can be computed like this: x of k is equal to summation n is equal to small n is equal to 0 to n minus 1, x of n w power n k in suffix capital N. If you see this formula, we can identify left side one component, that is capital X. The capital X is the notation where we use for frequency domain representation. Coming to the right side, we have small x of n. Small x of n represents the time domain. So, this is the input signal. Actually, our idea of DFT is finding discrete frequency coefficients for this x of n, and it was multiplied with a complex number, and its name is known as Twiddle factor. It will be represented by capital W power n k, in suffix we have n. So, coming to the values, how it is varying. The small n value varies from 0 to n minus 1, and the k value varies from 0 to n minus 1. So, what the samples we are giving in discrete, that many number of frequency coefficients we are going to get in frequency representation. So, coming to the exploration of W n k to the suffix n. So, in every equation we come across this complex term. So, writing every time e power minus j 2 pi n k by capital N is tedious or very difficult. So, to make that equation simple, in simple notation, we are representing that complex sinusoidal signal e power minus j 2 pi small k n divided by capital N within a general notation called Twiddle factor. So, we can see here W n k Twiddle factors equation. These slides will explain just as a representation. X of n W n k will give capital X of k. So, coming to the another way. So, in the first slide we saw that coming to time domain to frequency domain, we use DFT. In real time we have to use uh, all the signals or sequences in time domain. So, how to transform the frequency domain frequency coefficients into time domain? We have for that, so inverse discrete Fourier transform. Now, let us see how to compute endpoint inverse discrete Fourier transform. The notation of inverse discrete Fourier transform is IDFT, or we represent with IDFT. So, how to understand this IDFT? If x of k is in a finite duration frequency domain sequence with a duration of n samples or n frequency samples or a range of 0 n minus k, the variable here is small k, then we will compute that endpoint inverse DFT. The formula we can see here is small x of n, left side it is small x of n is equal to 1 by n summation k starts from 0 to n minus 1 x of k w minus n k n. Here we can see that left side it is in a time domain sequence. This inverse DFT will give time domain sequence. How to get this time domain sequence? By multiplying frequency coefficients capital X of k with a twiddle factor, but here the twiddle factor is the conjugate of the DFT value. So, that is why we notate here with minus, in the power we represent with minus n k. So, here we can see the representation of twiddle factor w minus n k of n. This is equal to e power j 2 pi n k by capital N, and we can see that with single word what is the main difference between DFT and IDFT is we have a basis function. We also call this twiddle factor as a basis function. The basis function of the DFT and IDFT are conjugate to each other. They are complex conjugative pairs. So, this is about computation of IDFT. Coming to the relation between endpoint DFT and DTFT. So, how this DTFT will be similar or will relate with DTFT? We all know that the notation of DTFT means, or the abbreviation of DTFT means discrete time Fourier transform. When it comes to DFT, discrete Fourier transform. What is the main difference? In DTFT, the time coefficients or time sequence is discretized, but the frequency coefficients are continuous. So, that is why we call that as a discrete time Fourier transform. Coming to the DFT, both time sequence as well as frequency coefficients both are discretized. That is why the time and frequency both are discrete. So, we call that one as a DFT. So, how to relate these two? So, we have in the previous slide we discussed about the formula of DFT with an x of n w n power n power w n k of n. By expanding that twiddle factor value, we can get e power minus j 2 pi n k by capital N. And here when we consider that term omega. So, omega is an angular frequency, that value is 2 pi k by n. If you replace omega with minus j omega, that means n is equal to 0 to n minus 1 x of n e power minus j omega n. That means if you consider that small omega in a digital, that is DFT. If you consider that one as a continuous one, then it is DTFT. So, we all know that the DTFT formula is x of n e power minus j omega n with the summation. Here the point is when you take the DTFT of x of n and make the value of omega discretize, then it is called as DFT, right. So, this is what the relation between DTFT and DFT. And coming to the problems,